In the world of physics, there are some ideas that feel absolutely untouchable. They're like the laws of the universe, written in stone. Well, today we're going to take a closer look at one of those sacred laws, the idea that the speed of light is always constant. But what if it isn't? Let's dive in.
Just think about it for a second. What's that one cosmic speed limit we all learn about? It's in every sci-fi movie, every physics class. Yeah, you already know it. It's the speed of light.
And there it is, that number, 299,792,458 meters per second. We call it c. It's the bedrock of Einstein's theories, this fundamental constant of nature that's supposed to be exactly the same everywhere in the universe, for everyone, all the time. It's basically baked into the source code of reality itself.
But what if that's not the whole story? What if that number isn't some ironclad universal rule, but more of a local guideline? That is the absolutely mind-bending idea we're going to unpack today.
Okay, so this isn't just some random shower thought. This idea is the core claim of a whole theoretical framework called the Unified Postmodern Theory, or UPT for short. And its proposal, well, it's a massive departure from what most of us thought we knew for sure. So here's the fundamental difference. Standard physics says C is just a given. It's a law of nature, period. UPT completely flips that on its head. It argues that C isn't a fundamental rule at all. It's the result of other, more fundamental conditions. It's what's called a local emergent property.
So, what in the world is an emergent property? It sounds complicated, but it's not. Think about water. You have a single molecule of H2O. Is that molecule wet? No, of course not. Wetness is a property that only emerges when you have trillions of those molecules all interacting with each other. UPT says the speed of light is just like that. It's not a basic property of space itself, but a property that arises from the conditions of a field within that space.
Right, so if C isn't this fundamental rule that's always been there, where does it actually come from? Well, according to UPT, you don't just find it. You don't assume it exists. You actually build it, right from the ground up. Here's the basic logic. Instead of just writing C into the equations from the start, UPT begins with something more basic, the total energy of a field. Then it mathematically describes what happens when you create a tiny little ripple in that field. And guess what? The speed that ripple travels at is the speed of light. And that speed is determined entirely by two local properties of that field, things the theory calls gamma and m. You can just think of them as the field's local stiffness and density. And this is the absolute key point. In this framework, the speed of light is not an assumption, it is a conclusion. The theory actually lets you calculate it with the expression c squared equals 2 times gamma times m. And what that means is, if the local stiffness or density of that field changes, then the speed of light must change right along with it. Okay, so this creates a really fascinating new problem. If c isn't a single fixed number, if it can actually change depending on where you are, how would scientists even talk about it? How could they compare results? I mean, that's the next logical question, isn't it? If you're a scientist and you go and measure the speed of light, you can't just publish the number anymore, because your colleagues would immediately ask, yeah, but under what conditions did you get that number? So UPT proposes a really strict set of reporting standards. To report a measurement of C, you'd have to list the core ingredients, those local gamma and m values, that stiffness and density we talked about. But you'd also need to report how much energy the wave is losing as it travels, a damping factor. And amazingly, even the physical boundaries of your experiment, like the shape of the container, become critical pieces of data. It basically turns a single number into a whole environmental report. And look, this isn't just about being extra thorough. According to this theory, the context of your measurement isn't just some background noise you try to ignore. It's an active ingredient that literally helps determine the result you get. So in the real world, a UPT report on the speed of light would look something like this. It's kind of like a weather report, but for a fundamental constant. You've got your core parameters, gamma and m. But you also have to note that there's energy loss and that the measurement was taken inside a curved boundary. And here's the craziest part. The final result isn't even a single number. It's a graph, because in this experiment, the speed actually changes depending on the frequency of the light. And that right there is the key insight. In the UPT model, things that standard physics might dismiss as just tiny errors or experimental noise, a little bit of energy dissipation, the shape of your lab equipment, are actually treated as fundamental variables that can directly change the speed of light you measure.
So, after going through all that, what's the big idea here? What's the main takeaway from this really challenging, really different way of looking at the universe?
It really all boils down to this. If a theory like UPT is on the right track, then asking the question, what is the speed of light, is kind of meaningless. You have to ask, what is the speed of light right here and right now? It would shift one of science's most solid constants into something that's dynamic, local, and ever-changing.
And that really just leaves us with this huge question to think about. What would it actually mean for everything we know about the universe, from cosmology and black holes to building computer chips, if the ultimate speed limit wasn't a universal law, but was more like a local bylaw that could actually change from one cosmic neighborhood to the next? It's a wild thought.